Okay, so today we are going to cover some forecasting techniques. Our buddy Piyush on YouTube is the guy that's going to run us through a series of videos. We've got the two different spreadsheets. One of them is the basic forecasting techniques using Excel. It's the instructor. That one's got the answers. If you want to follow along and do the math yourself, that's the student version. So we'll work with the instructor version here. And we'll just get Fuchs going.
And end this with
There we go.
hi, welcome to this video series on mechanics of forecasting methods. This is a series of 5 videos, and we will talk about moving average in the first video, and then exponential smoothing, trend lines, seasonal indices, and end this with measures of forecasting accuracy. So this is the first video on moving average. The moving average method is suitable only in the case where the data has random variation. In case there are trends or seasonality in the data, other methods are more suitable. And generally speaking, moving averages is only suitable for short-term forecasting. With this information, let's jump into the data with our numbers. Now, we have here data of 20 periods, 20 periods data and the actual demand. Now, if I plot this, I select the entire period, go to insert and a line chart. Uh, Here is the line chart. Let me change the axis. So select data and I edit this to say that the axis is actually the serial numbers. I select the serial numbers, that's the x-axis, and I say okay. And I say wonderful. I remove the serial numbers from here. So, okay, so now this is our data. Now if you see this demand, it's actually randomly varying around probably 135. Now this is a perfect scenario for moving averages. So let's say I have something called as 3-month moving averages. The forecast using 3-month moving average. The forecast for the fourth month is the average of the actual of the first 3 months. Let me repeat. The forecast of the fourth month is the average of the first 3 months. I will remove the Excel error. All right, so this is what is the forecast 140.33 and the actual demand 130. So the forecast for the fifth month would be the average AGE average of the fourth month, third month, and the second month. Bracket closed. Let me remove the error term again. The forecast is 139 while the average is 135. I drag this for the remaining part of the data to give us the remaining forecasts. We'll ignore the error message from Excel. Similarly, we could have a 4-month moving average forecast. So if I have a 4-month, the average for the fifth month would equal the average of the previous 4 months. And bracket closed. So the forecast for the month 5 is 137.75 as per 4-month moving average, while the actual demand was 135. So I copy this, Control C, and paste it here to get the answer. These are the averages as per the 4-month moving average. Well, there is a slight variation to these moving averages with what we call as weighted moving averages. So I put it WEIGHTED, weighted average. Now, in weighted average, let's suppose I do a 3-month weighted average. Let's say 3-month weighted average, 3-month weighted average, and I decide that the most immediate month, that is m minus 1, which is the closest. So in month 4, month 3 would be the m minus 1 month. I would need to give it a weight of 0.5. The m minus 2 month. So in month 4, the second month is the m minus 2. I want to give a weight of 0.3, and the m minus 3 month. So for month 4, the m minus 3 month would be the month 1. I decide to give a weight of 0.2. We should ensure that the sum of the weights is 1 because it makes our calculations a lot easier. So the forecast for the month 4 would not be a direct average, but would be equal to the weight of the um, previous month, m minus 1, multiplied by the actual demand of m minus 1, plus the weight of m minus 2, multiplied by the actual of m minus 2, plus the weight of m minus 3, multiplied by the actual of m minus 3, enter to give me a forecast of 141.7 units for the fourth month. I can just fix the cells of the weights. So since it's the column G, I fix up the column G, $4, $3, and G $2, and then control C and copy this formula to give me the weights forecast as for the 3-month moving average. We can have a similarly a 4-month weighted moving average. We can change the weights. How to select the weights, which method to select is an issue of probably some other video. And to end this video, you can actually plot the entire data on the graph by maybe just pulling this along to see how the various forecasting methods compare. I know this is a bit confusing, but fine, you can expand when you practice. And this can be used to decide which forecasting method out of the 4 or 5 or 6 in the moving average category we have to be used. I hope you enjoyed looking at this video. In case you liked it, please like the video on YouTube and do watch the other 4 videos in this series.
All right. So now we are going to go to moving averages and trends. We're not going in the order he had, but that's okay. So we're going to move from moving average to moving averages and trends.
Hi, welcome back. I am Piyush. This is part of the videos on mechanics of forecasting methods. Initially, this was supposed to be a set of 5 videos on the different methods and the methods of accuracy. This is a slight deviation on telling you a little bit more about moving average, and that's why we've called it video 1A. So the 5 videos are on moving averages, exponential smoothing, trend lines, seasonal indices, and measures of accuracy. Like we already said that moving averages, if you see the point B, is not suitable if there are trends or seasonality in the data. But we want to explore that point a little bit more. Let's look at this data here. Now, the first set of data which has been highlighted is a pure trend. So the demand in the first period is 34, 36. It's increasing by 2 units every time. Let us suppose I create a 3-month moving average. Okay, 3-month um, moving average. Let me copy this format so that it looks better. All right, 3-month moving average. So the average for the fourth month is the forecast for the fourth month. I'm sorry, is equal to the average of the previous 3 months. And then I will increase the font size to 14 so that makes it easier to see. You might zoom it to full screen so that you get a better view of the numbers. Now when I've copied the formula, what we see is that the forecast for the fourth month is lesser. than the actual of the fourth month by 4 units. And we see the same behavior throughout. Now 46 is lesser than 50 by 4 units. So what's happening when there is an increasing trend, the forecast is lower than the actual trend always, right? And the same case will be if we have a decreasing trend. So again, the 3-month moving average, let me copy this and paste it here. And I can even copy and paste these formulas here. Doesn't matter. What we see here is it's 106 and this is 112. It's higher by 6. This is again higher. This is again higher. So by 6 units always. So what we see in an increasing trend, this is an increasing trend, the forecast is lesser than the trend continuously. And in a decreasing trend, the forecast is higher than the trend continuously. So that's why we make this statement that the moving average forecast, it lags the trend always. Having said this, let's look at a new set of data to understand the application better. Now, this is a random set data. Let's plot this data. So the demand, I plot it, the 50 data points. Um, I plot them, I go to insert and plot a line chart. Wow, this is random data. We cannot make sense of it in any way. We don't know if this is a trend, is randomness. So to make sense of it, we take a 10 period moving average. So in 10th period, we take a moving average. So this is not a forecast. This is a 10 period moving average. So in the 10th period, we put an average equal to average of the first 10 periods, bracket closed, and we copy this formula here. We change the axis so that it's easier to see and make sense. Fixed it at 30 and say okay. So yeah, the y-axis now starts from 30. Now let me bring this new set of moving average into our data. And the first thing when I bring it into the data, yes, this red line, we now see that the red line is definitely showing an increase. So while when we had the individual data points, we could not spot this increase. There was a lot of random variations. When we created a 10 period moving average, these variations were smoothed out and the pure trend emerged. So what we see here in this data, which is a random data with trend, that it does have a trend in spite of the randomness, and this trend is clearly visible because of the average, the moving average that we calculate. So while we said that moving average methods lag the trend, but the moving averages help us identify the trend. Thank you for watching the video. Please share it and do like it if it helped you. Thank you.
All right.
Hi.
So now we are going to cover. So this is the trend line. He's going to cover trend lines themselves. This one's a little bit longer.
Hi. Welcome back to this video on mechanics of forecasting methods. I am Piyush. We have a series of 5 videos here. The first was on moving averages, second was on exponential smoothing. This is the third on trend lines, 2 more to go on seasonal indices and measures of forecasting accuracy. As far as trend lines are concerned, they're suitable for data with random variations and trends. They're not suitable for seasonal variations. And like all other quantitative methods, we use trend lines only for short-term and medium-term forecasting. Generally, we do not use quantitative methods for long-term forecasting. Let's jump into our first set of data. Data here is about takeoffs from India by scheduled airlines from 2003 to 2011. So in 2003, we had 263,870 takeoffs. In say 2006, we had 453,921 takeoffs. We will first try to create a linear trend line. A linear trend line is of the form of y equal to a plus bx. So here y would be the forecast or the demand where we use the past data. X is the year of interest, a is the intercept, that's the base level demand or the base level forecast. Graphically, a is the point at which the line would hit the y-axis, and b is the slope, or it's also the trend. So b is the growth year on year in the number of takeoffs. It's a very simple method to create a trend line on Excel. We first select the entire data. We have selected the labels so that it reflects in the charts. We go to insert, scatter chart, and then we select the first scatter chart here that has without the lines. We have the data here. Let me delete this label so that we may expand the graph. This seems more or less linear. We can put the cursor.
Now, Piyush is using an older version of Excel, but you should be able to follow on the newer versions.
Or any points. We can put it here, we can put it here. Right click and we get this menu. We select add trend line. We want a linear trend line, that's selected. The trend line name is takeoffs, which it takes from the label here. We want the forecast for the next 2 periods. We want the equation on the chart and also the R squared value. I'll tell you what R square is in a while, and close. Here is the equation for us. Let me take it here so that it's easily visible. Okay, so the equation is y is equal to 57,512x minus e something. Let me make it easier for you. I select this data, go here, format trendline label. These are numbers, and let's say we need 2 decimal places. Close, and let me increase the font. I select this, we go to home, we increase the font to 12. One thing we could alternatively do is make this a full screen so that you see the numbers better. So we have the numbers here as per the equation. Y is equal to a plus bx. Shift this here a bit. Y equal to a plus bx. So the a for us here would be a for us would be negative 114,931,084. So I'll write the number is negative 114,931,084. I'll ignore the decimals. And the B, the slope would be 57,511. We'll ignore the decimals again. So that makes it 512 rather if I round it up. So R square is one more factor which is there in the data here. R square tells you the strength of the relationship. It's called the coefficient termination. It varies between 0 and 1. If R square is 0, there is no relationship between the two factors we are comparing. And if R square is 1, it's a perfect relation between the two factors we are comparing. Since our R square is 0.94, closer to 1, we can assume a good relationship between the year and the takeoffs. So I can predict the takeoffs, the predictions that we have. So for 2003, my prediction would be equal to A, Y is equal to A plus B multiplied by X, which is the year, and enter. So the prediction was 265,452, which is very close to the actual. Let me fix the A and B, which is E6. So let me fix up the 6 part, and we also fix up this one so that I can double click this and create the data for us. So as for this, in 2012, the number of flights would have been 783,060. This is a very simple linear trend line. Well, trend lines need not be linear. Let's have a look at another data that we have here. This data is about broadband internet subscribers, again in India, per 100 people. So we have data from 2002 to 2011. In 2002, with 100 people, there were 0.01 people owning a broadband internet connection. And in 2011, we had 1.08 people owning the internet connection. In this particular example, we have replaced the year with a code. So 2002 is replaced by 1, 2003 is replaced by 2, 3, and so on. Is it compulsory for us to do it? No. I'm just trying to use it as another example of something different. We select the code and the broadband penetration. We've selected the labels again. We go to insert, scatter chart, the first set of data. Again, I will delete this label so that the graph expands. I put my cursor on any one point, right click, and say add a trend line. I can have exponential. You can try out with other formats here. We want the display equation. I want the R square value. Um, and I do not want prediction, but we can ask it to give us prediction for the next 1 period, 2 period, or 3 periods, or whatever. And I close it. Let me shift this label on a little bit on the left so that this equation we put it here. I'll increase the font size of this equation so that you can see it better. Perfect. The equation in exponential generally varies y is equal to a e raised to bx, where y would be the forecast or the demand, x would be the year or the code, and e is a constant 2.718. Um, Excel makes our task very easy. Let's understand what our a and b are. In this case, the a is 0.006, 0.006, and the B would be 0.5768, 0.5768. Right, so we have the A and the B here. So let's get to our prediction. The prediction would be equal to Y equals to A, which is this one, multiplied by e raised to. For that we put exponential. So it says it'll directly give us e raised to whatever we want. Bracket open, b multiplied by x. In this case, it's not the year, but the code. Bracket closed, enter. So as for this, the internet penetration would be 0.01068, which is very close to our actual number. I go back to the formula, fix up the A's and the B's, which is $3 and $2. Double click this so that we get all the values. So these are my predicted values or for the years. And for 2012, which is the code 2012, which is the code 11, you would get a forecast of 3.41 people per 100 people having a broadband connection. This is a substantial jump. Well, that's about it on trend lines. Thank you very much for watching. Do like this video and share it with your friends. My email is here.
Okay, we got one more here. Exponential smoothing. About 8 minutes.
Hi, welcome to the second video on mechanics of forecasting methods. This is a series of 5 videos. The first one was on moving average. This second video is on exponential smoothing. The third will be on trend lines, fourth seasonal indices, and the last one on measures of forecasting accuracy. I'm Piyush to take you through this video of around 8 minutes. Exponential smoothing is actually exactly same as the weighted moving average. Now, how this works is a element of different video. So everything that was applicable for weighted moving average is applicable for exponential smoothing also. And the points that we raised last time, that exponential smoothing, just like the moving averages, is suitable only for data with random variations. If there are trends or seasonality in the data, there are other better methods available. And typically, this is only used for short-term forecasting. Let's jump into the data. This is the same data that we had last time, 20 data points, which are varying randomly around 135. I've made the y-axis start at 120 so that we get a better visualization of the graph. We start. The alpha is a smoothing factor which we require. If you look at the screen here on the top left, there is something called as alpha. The alpha can vary between 0 and 1. The minimum is 0, the maximum is 1. We need this alpha to help us forecast using the exponential smoothing method. The formula is this one here. The forecast of the second period is equal to forecast of the first period plus alpha multiplied by the actual of the first period minus the forecast of the first period. This is the error term. So I'll repeat. The forecast of the second period is equal to the forecast of the first period plus alpha multiplied by the previous error. So the forecast of May would be forecast of April plus alpha multiplied by the actual minus forecast of April, which is the error in April. Like we said, alpha can vary between 0 and 1. We'll try to use various values of alpha and understand the behavior. Let's start with value of alpha as 0.3. No reason for taking this, just a random number, trial 1. We need a value to help us start, because if you look at the formula, that's actual minus forecast. I will use the average of all the demand numbers given as the first period forecast to help me start. Is this how it has to be done? No. Some people take the first period demand as, so this, some people will take this as 134. It can also be taken as the average of some 4, 5, 6 values. If you use the same concept over a period of time, it does not matter how you start. So let's look at the formula here. Forecast of the second period is equal to the forecast of the first period plus alpha multiplied by bracket open actual minus forecast bracket closed, enter. We get 135.05. Let's understand this first calculation here. It was the actual is 134 and forecast is 135. So what happens is the forecast of the second period is equal to forecast of the first period, which is 135.5 plus alpha, which is 0.3, multiplied by the error, which comes out to be negative 1.5. Multiply this by 0.3 and we get negative 0.45. When we subtract 0.45 from 135.5, we get 135.05, what we have here. We fix up the cell for the smoothing, the row $2, so that the smoothing factor is fixed. And after that, I can double click here to get all the forecast values for the 20 periods. If I click on the graph and extend this, wait for the arrow to come and extend, what we see is that the forecast is relatively smooth as compared to the actual demand, which has higher variation. So there's a smoothing taking place. Let's look at alpha as 0.8 to understand. This is the trial 2 to understand how this works. In this case, it would we start with the average of the entire period as our starting point. And then say same number we say equal to previous forecast plus alpha multiplied by bracket open actual minus forecast, which is the error, and say enter. And we fix up the smoothing factor, and then double click so that we get the values. Now let me include this forecast with alpha as 0.8. The green line, what you see in the green line is that it's more sensitive, it's varying. The variation is more than the blue line. So as alpha has increased, the ability to smoothen out the demand goes down. Let's understand this with two extreme values. Trial 3, we will do it with alpha as 0, which is the lowest value possible, equal to average of the existing demand values. We'll follow the same pattern that we have done. And then this period is equal to previous forecast plus alpha multiplied by bracket open actual minus forecast, which is again the error. We fix up the smoothing factor like we've always done and double click it. Now what you get here is that every period is exactly same. Okay, so it's completely insensitive. The first period forecast is the second period forecast is the third period forecast, irrespective of the actual demand. Now let's go to trial 4, where we take alpha as the other extreme, that is 1. We start with the average um, of all the demand. This is how we've always done it. So this is the first period. This equals the previous forecast plus alpha multiplied by bracket open actual minus forecast, bracket closed, enter. Let me fix up the smoothing factor dollar and double click this. All right, now look at this extreme. This was the first period actual demand was 134. The second period forecast is 134. The second period actual is 143. Third period forecast is 143. The third period actual demand was 144. The fourth period demand is also 144. Now, this is what we call as naive forecasting, which is a highly sensitive forecast where the previous period's actual becomes the next period's forecast. So what we have here, when alpha was 0, it was a very insensitive method. The forecast did not change at all, like you can see on the trial 3. And when alpha it's 1, it's a highly sensitive forecasting method, like naive forecasting, where the previous period's actual becomes the current period's forecast. We use this and some other considerations in helping us decide the value of alpha that we will use to forecast. I hope you enjoyed this video. Please do like this video on YouTube. Thank you.
Okay, so that is Piyush for this week on basic forecasting. We will cover some seasonal indices and some other issues next week in intermediate forecasting.